Thanks everybody for joining. Today here we have something a little bit different, a little bit interesting, certainly something to think about. Um, Especially, I think we're probably a lot familiar with the two if you go ahead and start sharing your screen. Um, the two extraterrestrial robots on the left of Brittan's kind of title slide here. Um, at least certainly I am maybe a little bit. I don't know I can say for certain what the left one is, but I know the helicopter, right? Everybody knows everybody knows the helicopter, or at least a lot of us have been paying attention to that. But thanks for joining us, and without further ado, we'll turn it over to Brittan Wilcox with a presentation or seminar today on robots and how that can relate to space exploration.
Thank you. Thank you everyone for having me. Yeah, I'm going to be talking a good bit about the two robots on the right. Well, the one robot on the right shown twice. In my talk here, rapid and reversible morphing to enable multifunctionality in robots, and then add on some potential applications for extraterrestrial exploration, mostly around the framework that drives the functionality of these robots and how it could have potential uses for space applications. And I will say, I certainly by no means mean to conflate some of my work with the two excellent robots on the left. I'm working at a very different technological readiness level here. Don't think my work is quite ready to go to Mars, but I hope you appreciate the what I'm going to present. And since, I think I'm still on the Zoom, not on the slides. There we go. And since I know probably no one here actually knows me, I just want to introduce myself really quick. I am a mechanical engineering PhD student, and I work for Dr. Michael Bartlett in that department, who is nice enough to let me work in his soft materials and structures lab. Also a tech undergraduate alumni, class of 19, again, in mechanical engineering. And you can see my terrible graduation photo there in the top right. And then also want to shout out the former undergraduate researcher who's also my co-author on this paper, John Joyce. So you can see in the bottom right on what was a less than great day of testing that we had on this project. So to give an overview of what I'm going to talk about before getting into some of the narrative of how it came about and why it's relevant to the framework for the novelty of the robot. What we've made is a multifunctional robot using a bio-inspired system that can rapidly change its shape between a driving state and a flying state. And we'll get into sort of why what's inside the housing is really interesting and has some interesting applications possibly for space exploration. But overall, what we've done is make this robot, and you can see in our diagram, we make something that can both drive, change its shape, however it needs to happen, fly, go through confined spaces, which, as you know, if you can't really fly a quadcopter drone through a tiny little tunnel. So it opens up a lot of modalities for a single robot to accomplish a diverse set of missions. But before getting into some of the novel work, I kind of want to talk about where this project started and what I was introduced to when I actually started as a graduate student, which was a prior morphing robot made by members of the Soft Materials and Structures Lab that worked in a very different way. This was made as a demonstration of a morphing metamaterial, which used low melting point alloys and elastomers and kirigami patterning to be able to change its shape through rapid deformation, but still lock its shape after changing. And the example in the drone was something where, on the left image of the drone, you can see it in a driving configuration. And it's rigidly held in that configuration by a metal structure, but through either strong deformation or heating, it can go into this flying structure that you see on the right side there, in which it's still rigid such that it can fly like a quadcopter drone. And I'll show here a video from that work where you can see a rigid drone drive up onto a plate here that it uses to do its functions. And you're going to see at high speed here, what it's doing is it's heating and melting the low melting point alloy, and then now cooling so that that becomes rigid again, and then it's going to fly off any second now. There you go. So that was the first work, and we had reason to continue and try to make that better. So I came in with new goals for the next work. In this case, what was this original drone only really could do the one shape change, since it's using gravity to sort of fall into that flying position as it's on this pad that provides the power for its heating of the metamaterial. Additionally, you can see it requires the pad. We wanted all the systems to be on board to operate completely by itself and be able to go anywhere. And then, of course, we want everything to be faster. I think, maybe on the last video you saw the point where it said 50 times speed. It takes a lot of time to heat up and cool down and switch between its states. So, the initial idea, and this is where I came into the project and took it over, there's some people who wanted to use shape memory alloy wire to pull it into its various configurations. And lock it into either its flying or drying shape. And I'm sure probably most people are familiar with shape memory alloy wire, but the 10-second description is that with temperature it undergoes phase change, and in a wire form that means you can apply heat or electric current to it with joule heating, and it will shorten and apply a force as it shortens. So the idea was apply current to the wire, have it pull on the sides, and make it change its shape. But as you can kind of see from some of those terrible pictures on the right, in the early days of the project, it resulted in something that was becoming pretty bulky. It wasn't going in the best direction. We weren't sure if this was going to be the right solution. And, kind of stepped back and asked myself, what is the best design solution for this? And as we moved on to some other things, this is something that kind of came up. This design, which just used shape memory alloy and springs to change its shape, and I've got some videos here to show. I'm gonna mute my output there. You can see it quickly changes its shape in a small form factor, and can go back and forth. And it uses this mechanism here where the shape memory alloy sort of acts on a very short lever arm to pull on it, and the springs act at the end, so that when nothing's happening, the springs are holding the system in place, and it achieves with both sides of this bistability. But it also means that the shape memory alloy, which has a short stroke, can pull it to the midpoint, and then the springs can take over and make that shape change very rapid. You see sort of the path of motion labeled there with this system. And we kind of moved forward and used this for the bistable shape change of a multifunctional robot, but we also looked to see, how can we characterize this system and describe it? And that led to, what I think will be the main focus of my talk, and I think the potential applications for space and this kind of robotic morphing is LaMSA systems. This is a framework that largely came out of the biology community, studying some various insects in nature, such as the jump of grasshoppers, to look at systems and describe them as being latch-mediated and spring-actuated, in a way where a motor can put energy into a spring over any period of time and significant amounts of energy, surpassing the single-stroke work limit of the motor, and the spring can be held in place with the latch and then unlatch, and all of that energy can be used in a very short period of time due to spring actuation. And it kind of creates a lot of new possibilities. But there have some some limitations and places where it works and doesn't work. I'm not going to give everyone the basic physics lesson, but we know sort of the relationships between power and force, and we know that motors have a work limit that they can apply any time, a power limit, but springs, if you apply a lot of energy into them, can hold that energy and release it very quickly. And we get sort of this plot from one of the leaders sort of in looking at this field, talking about sort of the application spaces for spring-driven and motor-driven systems, basically putting in the theory that a spring-driven system is going to be better than a motor-driven system at very small scales. Whereas, you hit a certain scale and the motor-driven system is going to work better for what you're trying to do. And I think that's one of the interesting things I'm going to get into sort of in the application space, because I think that there are ways we can think about these kind of systems and apply them to many different types of robotics that goes beyond that simple idea. And just for a little bit of fun to kind of tie up the background LaMSA systems, there's a lot of animals that are examples of this, usually in the realm of insects. But we also have plants. You can see the Venus flytrap there. That is an example of a LaMSA system. It's snapped through to close its mouth is a spring actuated motion. And the latch is triggered by the landing of an animal in it. The grasshopper, another great example. It can store energy in its leg over a period of 300 milliseconds, but then release it in just a couple milliseconds. So you get all that energy from muscles being used in a much shorter time period to achieve a much greater output. And then what is kind of the beloved child of most of the biological LaMSA studying community is the mantis shrimp, which is a unique animal that has an appendage that you can see in the bottom right that has a mechanism by which it can either, depending on the species, spear its prey or smash shells of its prey or stun its prey in various ways by using a spring-driven limb. And you got a video here showing at 1/5000th speed just how fast this kind of motion can happen. So it uses, this is the smashing one, and it uses this to smash the shells of its prey to get it, the meat inside. And at a small scale, what is a pretty violent hunting action, but we want to know how can we use these kind of systems to better make engineered systems. So moving on, we have sort of the design that we had in the end for this morphing robot, still using this bistable system, and being able to make a system that has parts somewhat enabled by some of the recent last couple decades advancements in 3D printing, being able to enabling us to make new things in new structural shapes that we haven't before. But you can see here we have basically three components in this upper left diagram. We have the central frame, which rests within the body of the robot, and then the green two outer links, which attached to what is in the images of the robot, the red, what I've called wings. I don't know if there's really a better name for them or not, but that's what I've used to create a system where by applying power to the set of SMA wires on sort of the top of this frame, it can move from one position to the other, and by applying power to the ones on the bottom, it can move back. And for a little bit more details on sort of how this is accomplished, showing sort of one single actuation here from some of our high-speed video. Starting sort of in the bottom position there, where we could call the driving configuration in the ultimate robot. Current is applied to SMA wires sitting on the top that pull on that short lever arm that I mentioned. And there's this period of joule heating, and then the SMA will cause this this lever to move and eventually hit this midpoint. And at the midpoint, the direction of the torque that's being applied to the spring around that hinge reverses. And this leads to what has been called by some a torque reversal latch. And that's sort of the latch of our LaMSA system. And then the spring, because its intention has a good amount of stored energy, makes the rest of that motion very fast. And it just kind of snaps to its new position. And of course, because the spring's holding it in place, it no longer needs power, and it can just stay in that position securely without any power being applied to this morphing system. And there is, one set of wires for each direction to do this morph. So now I'll show the video of sort of this in action. So you're going to see it's very fast. And there is the red LED at the bottom. That's our current indicator of when power is applied. So you can see it turns on a little bit before. So it has that initial joule heating phase for the shape memory alloy, which its phase changes around 70 Celsius. but once it gets up there, it moves pretty quickly. And then, yeah, here we have our high-speed video. And really, once the SMA gets up to temperature, you'll see there's a bit of an initial ramp-up period to the motion, but even the SMA moves the system pretty quickly. And yeah, it's just on loop here. But yeah, and then I'll note, there is sort of the time between the two motions. So since it's SMA, there is sort of a temperature cycling. It needs to cool. It needs to return to its initial phase. So there is some limit to how quickly you can sort of do these one after another, on order of a few seconds. But I think it still has, it's still pretty neat. So showing some of the data from that, you can see sort of the timescales and speeds we have of this system, showing that most of that shape change, you can see kind of the initial ramp up period um, of the motion, but most of it occurs in about 50 milliseconds. So this is able to change its shape very quickly. And we measured a maximum angular velocity of 12,000 degrees per second. So we thought that was pretty good. And you can also see some of our power metrics here, using a few watts for about a second, and that's it. And that doesn't need power anymore after that. In terms of energy, it's about 11.5 joules of energy for a single shape change. And then at the bottom, we just wanted to show this is very reversible. So you can see we did it 100 times consecutively, going back and forth, and every time it was successful. So it's able to be done continuously. A lot of LaMSA systems kind of end up being one-time use before you need to get your hands in and reset this. But this, no hands-on, did it 100 times back and forth, is a pretty robust system. And just comparing this a little bit to some of the other robots that have used this system, our work takes fractions of a second. And there are a few other works that have done shape-changing adaptive drones using motors. And you can even see the previous drone there. It's the purple bar. It takes the longest to change between its shapes. Even then, it's only sort of a one-time thing. So this kind of system allows a lot of performance increase, be able to do things very rapidly in a way that is arguably simpler because you're not involving any traditional motors. And then here, just again, a little bit more clarity on sort of how it fits in. So you can see an image here of what is the internals of the morphing system in the robot, but with the motors and propellers on there, and how it's structured. And then sort of on the right, what the ultimate robot looks like. And it uses that system that we've been looking at to switch between this flying shape and the driving shape. And with this, we were able to make something that we made this obstacle course. And I know this space applications. We did search and rescues. We kind of tried to make it look like a destroyed building or something, after a tornado or whatever. And you can see it can drive, quickly change into its flight mode, and then sooner or later it's going to take off. I will admit I'm not the best pilot, so you're going to see me struggle a bit getting it over our wall obstacle, and we can land it on the other side, and it's going to change its shape again. This is all manually hand controlled, and then it's going to drive away again. And it can do sort of all of these actions in any sequence, however you need, for whatever kind of operation is necessary. And I'm sure, and yeah, here we go. You can see here kind of, again, the whole description going through this tunnel that, a normal quadcopter drone wouldn't really be able to fly through, going over a wall that a normal driving robot wouldn't be able to get past. And, being able to do these things repeatedly for whatever the need is. And I think, for this alone, the space application would be, we don't necessarily have the most structured environments in extraterrestrial locations. So perhaps, this kind of multifunctionality could be helpful for those. But as I'm sure everyone saw, there are some interesting things attached to those motors that we had to make, which is just a drone propeller combined with a wheel structure that we had to come up with to make it be able to do both of those. And we wanted to be able to do it on a single motor to kind of show how this kind of robotic shape change and our morphing mechanism can enable less complexity in robots. And we're able to get something that's actually surprisingly performant. You can see this thing was able to get up to in some of our tests, almost 10 meters per second driving, and considering its size, which I mean, I'll just show you, it's about this big. Driving, its size, that's over 40 body lengths per second driving. It's pretty fast. It zips. But most remarkably, the cost of transport, and this is saying, we looked at other papers doing similar robots. This is a very low cost of transport energy-wise for being able to traverse great distances, and it's much less than what it is in flying. So it brings in an additional benefit of um, being able to perhaps drive great distances to perform flying missions while retaining most of the onboard battery, being able to do what you need to do and open up sort of new possibilities. And then on the right, we also sort of show the thrust that we get out of this. Examining, does adding this extra wheel structure to the propeller reduce the thrust that we get out of this? And you can see a small reduction, but ultimately not impactful to its ability to perform. It still has reasonable parity with the original stock propeller meant for drone flight. And a dash line representing the weight of our robot, showing that we do get thrust reasonably well above the mass that we're doing. And I guess I didn't actually mention cost of transport metric that we used is power in time divided by the mass times gravitational constant times the velocity that you achieve. So moving on, oh yeah, just a little video here of that fast driving I mentioned. So here we go, tennis court starting from 0 and just letting it scoot. And then also just showing we can fly it as well. I mean, I'll admit, after it got out of frame, I did kind of run into the wall there. That's shortly after is where that picture of my co-author I introduced at the beginning was taken. So we are able to get a pretty performant robot in both of its modes. So to kind of get into this and what I think some of the interesting novelty here, and then get into the space applications, what we talked about, outside of the space regime where we were initially doing this is, we talked about how LaMSA theoretically has been most useful at very, very small scales. In this case, this example in the chart here is considering, a projectile, right? And saying that, it is sort of less than 10 grams is where that transition between a motor being the most performant thing and a spring being the most performant choice switches over. We could say, we have a robot that weighs about 450 grams, and we've put a LaMSA system in it that gives it very unique functionality and capability. And in terms of, how quickly it changes its shape, better performance than a lot of other motor-driven robots in literature. So we think that perhaps giving additional consideration to LaMSA systems in robotics as individual components of larger devices is a way that we should be thinking about both those kind of systems and how we can develop robots to give them the best performance. And of course, we've in this one suggested using a bistable LaMSA system to enable multifunctionality such as the flying and driving that we show here. But certainly there would be plenty of other applications where a switch between bistable states using a simple and quick system would be beneficial. And then just, to get into a little bit of where I see, and I think this is potentially applicable to space uses. And, I'm a mechanical engineer. I'm not an aerospace engineer. So I kind of just want to bring it up and see what other people think and see where it can go. Because there's not too much work yet in the space applications of these systems. It's an area that's been growing in both the biological and engineered side. And besides just putting an astronaut suit on a mantis shrimp and sending it to space, how can we make use of these? One application coming from Dr. Hawks's group was this engineered jumper that they published in Nature that was able to jump very, very high. It's very lightweight. I've actually gotten to see it in person. It's a very interesting device. It is probably about that long. It compresses and then jumps. But they had the idea that it could be used for lunar exploration because you could sort of angle this jump and jump, meters and meters from perhaps one crater to another to explore various areas, that would be very challenging to get a wheeled vehicle into. You're certainly not getting a flying vehicle into there on the moon, and a lander you can only get to one. So an interesting application as we think about sort of where these could be useful for the future. But I think where space applications could really be interested in this is you get interesting performance at the small and light scale, without using motors, perhaps without using motors. I think there are cases where using a spring instead of a motor-driven system could reduce design complexity. Something less complex weighs less. I'm sure a lot of people, much easier to fit on the rocket taking it up there. And then perhaps, in the case of, the engineered jumper proposed by Hawks Group, it enables a capability that would otherwise be very costly. If you want to explore many, many spots on the moon, you need to either make a very, very capable wheeled robot, or you need to put down many, many landers. So it brings in some interesting possibilities for what you could do. And I want to see what other people's ideas are, because I think there's a lot of places it could go, and I want to kind of get this out to the space exploration community to see what y'all could come up with as well. And with that, that was the talk. Thank you everyone for listening. If you want to know more about what we do in the Bartlett Lab, it's actually a bigger variety than that, and a lot of things very different from that, but we have the QR code or the website. But I'll open it up to questions.
Questions here? Any questions online? I'll maybe open, not necessarily a question, but a comment, since you're kind of asking for open discussion. I think this is very interesting. Right, one of the things with the Mars explorers, right, is that they had the combination of the helicopter and the wheeled robot, especially with flight, not even, not only being able to get over the top of things, but just doing like an aerial surveillance. And actually a bit of like sci-fi reading this story about something very similar to the, I'm trying to remember where the helicopter and the the most recent.
Ingenuity is one of them.
Helicopter. But yeah, but it was sort of similar to that, not exactly. But the idea was that they like the robot, like the helicopter, would just go out and then do this like aerial surveillance, and then the wheeled one was actually, its mission was to go to a previously landed robot and see, like, it was defunct, and like try to go and like fix it type thing. And so doing that like navigation, where but the imagery might not be so good, and like if it comes up on an obstacle, it could just hop over, short of its route. So that's a interesting thought and kind of application sort of for this. It's kind of really fun to bring this up, because like I said, I've been reading that, it's telling the story about the robots kind of doing that. From the robot's perspective, it's kind of really interesting part of that. But yeah, so and certainly, the other thing, the improvement I can see is just somewhat the power, right? The melting is a good thing, but yeah, that takes a lot of energy too, just to melt metal to make it do something.
Yeah, I know there's one, I think, hand up in Zoom. Do you have a question?
Yeah, thank you. So, really interesting. I was
Wait,
trying to
am I-
think.
For somebody.
Okay, sorry, I think I have my speakers muted. All right.
Hey, so my question was
still am not
associated
hearing
with.
I don't know what my audio output device is actually.
TV. Hold on there, Austin. I can see you're trying to talk, but
I can drop something in the chat if it's easier.
Can you try again?
Can you hear me now?
Yes.
Awesome. All right. So, really interesting work. I really appreciate you coming and talking to us today.
Thank you.
Couple questions. One, has anyone done a study trying to determine the mass savings of this kind of SMA bistable actuator relative to a conventional actuation system?
I mean, yeah, we looked into it a little bit. I don't think it was something we came up saying, was, relevant to speak about too much. I know our system specifically was about 50 grams, but we weren't particularly trying to optimize for
Understood.
ideal mass to performance ratio. I think perhaps, I don't know, I didn't test what a comparable servo motor or something would be to achieve this kind of performance, but yeah.
Yeah, I think that may be an interesting differentiator for the space world, is both a volume and a mass story there. Though that's probably a further investigation. A question that I would ask, that maybe where these actuation systems provide really unique capability in the space environment, is through leveraging and tuning your SMA alloy for passive actuation, where you allow the natural environmental thermal changes to
Yep.
perform that actuation for you. Has there been any thought to leveraging the system for passive changes or passive actuation, or has it mostly been active?
I think most of the work that's been done has been active. There is not too much work in the field as it is, and a lot of the work has been from the biological side. There's a good few papers that sort of are trying to emulate biological systems with engineered systems, and then other people making jumpers. That said, there have been a lot of things that look at different ways to do latches. I don't know if I can speak specifically thermal control and SMA as sort of a latch mechanism to create these motions, but I know there's been some work about swelled polymers and using evaporation to create buckling in the polymers to create a latch and a quick motion, which is actually kind of similar to what the Venus flytrap does, interestingly enough. So there's been some interesting work sort of scattered here and there using very different latch mechanisms, but most certainly, I mean, the thermal control to trigger the SMA, I can't think of any one in particular, but it could certainly be done. And, I'd love to see it. And so just to go back on the first question, there's one other thing I will mention, I mentioned sort of the scale of this robot. I will say, I mean, this system is scalable to much smaller scales if we wanted to. The limiter we had was actually the size of our electronics that we had, because, we're not an electrical engineering lab. We couldn't necessarily custom design boards to fit exactly what we needed. There's a reason I'm not showing you the internal wiring of this robot. It's a mess. But theoretically, with some of the smallest boards that you could make that could still control something like this system could get down very tiny as well. And of course, then we're talking low mass. So just give some added context in that question about weight and volume.
Very interesting. So you talked about the efficiency of your air transport. Did you do the same calculation for ground transport?
So the high efficiency, I will get back to that slide right here. The high efficiency was for ground transport in this case. Our air efficiency, I list that here. We were only really able to get one test of that, just due to some of the circumstances around our testing. But in that one, we were measuring a much higher cost of transport. I know comparable, or maybe not comparable, but some other drones at same size have much better cost of transport. So our system, as we designed it, wasn't particularly optimized for that. But yes, we did look at the efficiency of both.
And what's the difference between your ground version and their air version, or state-of-the-art air cost of transport?
So our ground version, I think, is still better. It's not by nearly as much of a margin. I do not remember off the top of my head what some of the other, just quadcopter drones at the same scale had for their cost of transport, but we do beat it out by a smaller margin than what we beat out our own air cost of transport.
Understood. Thank you.
I think sort of along those lines, I'll the comment on the question in the chat and kind of phrase it. That there's a kind of interesting. It was good to bring this up because that was one thing I was looking at, especially thinking of extraterrestrial exploration. One of the next areas, right, is looking at the wheel design that you have here. In doing that, how do you make it a good wheel for a lot of different surfaces, but as well try to optimize that, right? So the question is more of any kind of consideration on the kind of survivability or things like that. How would you, do you think, how do you think that would kind of impact things?
Well, I mean, yeah, fully agree. The technological readiness level of this is a very low number.
Yeah, with the wheel, you can see is not the.
Yes, the wheel is a sheet of polycarbonate laser cut into a circle and Loctited to a drone propeller. I won't make any ifs, ands, or buts about that. Yeah, there are a lot of interesting applications, like ways it could go, things I've thought about. I think the motor is actually one of the bigger limiters, right? With these kind of motors, you don't necessarily get the speed you need plus the torque you need in one package. And we were also somewhat limited by what we could get our hands on for this, because we were using mostly proprietary electronics. So these are just kind of stock over-the-counter drone motors. But I mean, I've had thoughts about doing multi-material 3D printing to make this kind of structure where it's a rigid polymer throughout the propeller, but then something more rubbery around the edge to give it, like a traction surface. We did do some small testing with that, but ultimately we didn't really go down that road with this paper specifically. Did that answer?
Yeah, I think so.
Was there anyone else in the Zoom who had questions? Oh.
Yeah, I do have a question and some thoughts. Good job with your presentation. It's really interesting to see all the work that's being done at Virginia Tech in general.
Thank you.
So I guess a comment is I see a potential application to your kind of concept here as like a balance between size and maneuverability on like a rough surface, because typically when a rover's launched, it's pretty large and the tires are very robust and it's got a good system so it can go on really uneven terrain or steep hills and things like that. What's interesting about your approach is perhaps that there's a threshold between, having a ground vehicle and the steepness or ruggedness of a slope, where you'd want to go into drone mode versus cart mode, and you wouldn't have to make your ground vehicle as robust to all the incline changes, but you could also have at least some functionality in like driving on the ground for power, because I'm imagining that it's a lot less power intensive to roll something on the ground that's going up in the air. But it looks like you have some like cost analysis done, that previous slide of looking at power consumption and speed and such. Have you actually done these for different values of G, like on the moon or on Mars or something like that, where you have a different planetary body to kind of see like what's the trade-off between having it be in drone mode versus like ground mode?
No, have not done that. That would be interesting. I mean, it would be a relatively simple calculation. One thing we have done, as I look through my extra slides, which there are far too many of, since you brought up comparisons, yeah, we did do comparisons with other works we saw of similar sort of multifunctional robots. So, for us, we were able to get, a very low cost transport and high speed relative to other works. As to whether that comparison bears itself out for other extraterrestrial bodies and certainly different atmospheres, that is one thing I was wondering if I would bring up, how small the propellers on this thing are compared to what I think it was the Ingenuity helicopter. I remember they had to make extra large blades for the thin atmosphere, so I can't say if I know how that would affect it either, but yeah, no, that's an interesting thought. Thank you.
And Yeah, I have interest / some experience with doing like custom hardware design and things, so perhaps we can have a follow-up conversation and maybe talk about some potential collaboration, so.
Of course, thank you.
Well, I can just say we were kind of interested in this design because of our senior design project is a human-enabled mission for Venus.
Mhm.
And so we were looking at working drones, the ground being so hostile and the atmosphere being more stable, I guess. Kind of working between those, but ultimately, I don't know if there's anything that can handle the extremes of Venus at this point. It also has its design, but it was definitely interesting just to learn more about it.
Thank you.
Anything else online or otherwise? We get a couple minutes of our hour blocked off back.
Yeah.
Going once. Twice. Well, thanks everybody for joining today. Again, great presentation. This is really interesting, and you or other students can come back and share some more because this, yeah, like I said, this is really kind of a fascinating kind of work. So a round of applause. Thank you very much.
Thank you.
And we'll have actually, I usually do Space and BT seminars every 2 weeks, but due to some scheduling things, we'll actually have one next week from one of our former PhD students who's out in Colorado. I'm hoping I can drag a description out of them in the next day or two and get that out to everybody. So, otherwise, for those in the room, take a cookie and maybe see you next week.
And thank you for having me and letting me present something that isn't quite as space related yet, as I'm sure most of your presenters are.